Greetings and welcome to a new video about electric circuits. We continue with another topic which is also very important, maximum power transfer, and we will use our knowledge from Thevenin's theorem for this example. Of course, we'll look at our calculation step by step and also verify these in SPI simulations. So before we move on, I would like to first briefly discuss what is maximum power transfer and in what condition do you have that maximum power transfer. For instance, you have two circuits, circuit A and circuit B, you connect them to each other. How can we then transfer the power from the circuit A to B in a most efficient way? That is actually the question in place here. So we have a voltage across the terminals of this circuit B, and also there will be a current flow into the circuit B. And we would like to maximize both of them, or actually find the optimum value to get the product of these two as large as possible. So the maximum value of these two together as a product. So many circuit applications require maximum power available from the source, for example the circuit A, to be transformed to a load resistor. That could be, for example, this circuit B. Now, power transfer can be discussed in terms of efficiency. So the more you transform from the circuit A to B, the higher is efficiency. That's why it is very important to discuss this topic. Now, we can model this. We can say that circuit A and B can be modeled as such. We have, for example, a voltage source in series with a resistor. And that is what we also have discussed in the Thévenin theorem, where we have a voltage source in series with a resistor, which is then a Thévenin resistant voltage and Thévenin resistance. And this is now actually the representation, a model, very simple model of circuit A. This can be also done using Norton's equivalent circuit, where we have a current source in parallel with the Norton resistance. This circuit B can be modeled by just a load, but it can be of course more complex when you have frequency dependency, but in this case we consider only DC analysis, and you can then model circuit B by just a load resistor. This will be then our source and this will be then our load, so we connect them to each other, and we would like to have actually between the node X and Y, so across the load resistor RL, the maximum power from our source. So how can we do this? Now we have of course the current and the voltage across this. So let's then begin with the basic equations we know. We know that PL, which is the power delivered to that load, is IL squared times RL. We can also say, okay, the current in this series circuit is given by IL. That is exact same current delivered by the source, VTH, and also current through RTH, which is exact same as load current because they are series. So we can say VTH, which is the Thevenin voltage, is equal to the divided by the total resistance in this circuit, which is then the summation of these two resistances. We can now substitute this IL in here in the expression for the load power. So the PL is then equal to the IL squared and then given here in the Thevenin voltage over the total resistance in this circuit times RL still. So how can we maximize now this? This is actually the problem in this case. So we will do that mathematically. So we can now also incorporate this square in the numerator and denominator, and you can see the expression here. And we would like to write it down in this form because we would like to see what kind of an effect this load resistor has on the power transfer. So I will keep actually our voltage delivered by the source, let's say, as a constant, and then we'll only look at the RL. Now that means actually I need to differentiate our PL towards RL. That's the only thing I want to change, and then see how can then this, the PL, be maximized. In order to do that, you differentiate this function, which is of course a function of many parameters, VTH, RL and RTH. We consider the RL is only changing Then we can use this, and that is then given by this expression. You see, this is a constant, so we can keep it in front. And now I have used the rules for differentiation for a fraction, for a quotient rule. So we can see this is then differentiated, that's just 1, times the denominator, that's actually shown here, minus this part, numerator, not differentiated, times the differentiated denominator will be then 2 times the RL plus RTH, which is actually shown here. And then you divide by the square of the denominator, that's actually shown here. So that's the total expression for our differentiated PL. What we want is we want to find the maximum value of the PL. That can be done by finding actually the value of this slope is 0. And that can be done by equating this to 0. This is 0 when the numerator is 0. So we can say this numerator can be equated to 0. So it can be done in this form. We see actually two terms, they are the same. So we have RL plus RTH. So we can divide it out. You lose one R plus RTH here, and you also lose a square here. So we'll get actually this expression. Now what you see is actually very interesting. RL is equal to RTH. So the load resistor must be equal to the Thévenin resistance. Very interesting result. So maximum power transfer will occur when the Thévenin resistance is equal to the load resistance. This is a nice result, and this will be then used in our example. Now, before we move on, let's look at it in more detail, the maximum power transfer again. Now, we can consider, for example, a circuit where we have this as 10 volts. We already calculate, for example, from a very complex circuit. And also the RTH, that is the Thévenin resistance, is also calculated or given as 4 ohms. Now, we can now generate a table for this situation. We can say, okay, this current IL, which is flowing here in the series connection, is that total voltage divided by the total resistance. The voltage across the load is then calculated using Ohm's law, so IL times RL. And the power is then calculated using IL times VL. So these are the basic formulas we need. Then we can generate actually a table. So we can say, okay, let's then change the value of RL and see what's happening with the three values. Of course, we are interested in this last column, which is the PL, the power of the load. But let's see what's happening. So if I now say I will keep that 0, so let's say the most smallest value you can have for the load, just a short here, then you will get a 0 ohms. That will be 2.5, because then you will get 10 volts over 4 will be 2.5 amps. And you get 0 volts, of course, across this shorted wire, and you get 0 watts power transfer to the load. Now, if you move on, you can say, okay, let's make it 1 ohm, and then you can see that the current is decreasing. That is logical, because then this value in the denominator will increase. And your voltage drop will now increase, and also power transfer also will increase. So you go from 0 to 4 watts. Now, if I increase it again, for example 2, you can see the current is also decreasing again. That is logical. And also the voltage is increasing. And the power is also increasing, but not that much, because we went from 0 to 1 ohms, and then the power went, let's say, 4 watts in the plus direction, but now it's only approximately 1.6. So not that much. So we see actually there is something happening. It's not a linear relationship. Now we go to 3 ohms for the load. We can see it is almost 1.43 amps. Again, the current is still decreasing, that will still decrease, and the voltage is still increasing, but I also see a smaller increase again for my power. Now let's move on and go to 4 ohms, because we said the load resistor must be equal to the Thévenin resistance, and now is the place where we need to see sort of the maximum power transfer. Now 4 ohms, 1.25 amps, 5 volts, again for the loads, and 6.25 watts for the load. What happens if I now increase the load further? So if I go to 5 ohms, that will be then, the current is still decreasing because the denominator is increased again. The voltage also increased, but the power is decreased. You can see it is not 6.25, but it's 6.17 approximately. So increasing the load resistance will increase definitely the voltage across it, but also decrease the current, and the multiplication of this one, the product, will not be larger than the case for 4 ohms for the load resistor. And if I move on and show you actual result, you can see actually it is decreasing. So you can also see this value is decreasing. Keep decreasing if I go to 8, if I go to 9, and if I go to, for example, 10, you can see what's happening. So this is really the optimal value for the load resistance. So this, and given in bold here, is actually the proof that RL is indeed must be equal to RTH in order to have the power transfer maximum. And that is also given here in the red box. Okay, now these are the plots for this specific situation. We can see the IL is starting at 2.5 amps and then keeps decreasing. And I just only plotted from 0 to 10 ohms for the load resistance. And it goes actually all the way to 0.714 amps. And this will of course keep decreasing when you increase your load. And you see also the voltage increasing, going from 0 volts up to 7.14 approximately. You can see that also from the last row here. But the power doesn't make actually that increase. It gets of course some maximum value and then decreases when you keep increasing your load. So this is really your maximum value, and that happens at 4 ohms. So load current, load voltage, and load power. This is very important to see that there is indeed an optimum value for your load power. But let's see that now in more complete example, and this is the circuit I will now discuss, also discussed actually in the other previous videos. Now we would like to do the complete business from scratch and then consider actually the power transfer, the maximum power transfer. So we would like to calculate the required load resistance to transfer the maximum power to the load. For this circuit, we know the VS, R1, R2, and also R3. So we don't know RL. That is the question in place here. And again, the currents and also the voltages are given here for later discussion. So let's go to the solutions, and we can say, let's then use, for example, again, our Thevenin's theorem, and then make the load resistance equal to the Thevenin resistance. So we can say, let's then go to step 1 and then remove the load resistor, what we have done also in the Thevenin's theorem, and then get to this circuit. And then step 2 is determine Thevenin voltage. That is the voltage across the X and Y nodes. And note, no current will flow again through R3. So we can say, using voltage divider rule, we can say R2 over R1 plus R2 times Vs is the Vx. That is the voltage at this node, which is also the VTH. And if I now substitute the values, 60 over 100 times 10, you will get 6 volts for the Vx. And Vx is also V for the Thevenin voltage. And now Thevenin voltage is now 6 volts. Okay, now we determine now the Thevenin resistance. That can be done by disabling all the sources. In this case, we have only one voltage source, so we disable that. That means a short, so your circuit becomes this. You again look between these two nodes inside, and that is your R Thevenin. Okay, I see actually R1 and R2 in parallel, so we can combine them in this form, and that will be the combination. I just call it RP. So RP is R1 in parallel with R2. That is this formula, and that will give you, if we do the math here, 24 ohms. That means your circuit now becomes RP in series with R3, and that is actually your R Thevenin. Then we get this, and if I now substitute the values given here, that will be 44 ohms. Now, we will now form the Thevenin equivalent circuit using the VTH and RTH we have determined. This is the most important circuit, or equivalent circuit in this case, in order to go to the required load resistance, because we know it is 44 ohms. Now we can move on and then say how much is this. That is of course very easy. We need to also make the load equal to 44 ohms. That's actually our answer here. But let's move on and also see more details. Now we now connect this here and also have the polarities for the current and the voltage. Now for maximum power transfer we require this. We already said that. That means we have now RL is equal to 44 ohms. So we require for this specific circuit, the load is 44 ohms to have maximum power transfer. Now power relative to the load is given by this expression or by this expression. That doesn't matter which one you use, but using voltage divider rule, we can say the VL is equal to RL over RTH plus RL times the VTH. Now 44 over 44 plus 44 times 6 will be then 3 volts. So we see again, it must be 3 volts for that specific situation. And I can say, now the PL, using this formula for example, is then 3 squared over 44. That will give me 204.5 milliwatts. This is the maximum power I can get from this circuit configuration in this load. Okay, now let's also look at the simulation results. This is what we have determined, and this is now the circuit I have prepared in the simulator. You can see the voltage source of 10 volts and also the R1, R2 and R3. And this is the current meter. It measures the current from left to right in a positive fashion. And this is the load of 44 ohms. And this is now also the voltmeter to measure the volts across our load. Now, if I now produce voltages and current stable in the simulator, you can see the IL gives me 68.2 approximately milliamps, and also VL gives me 3 volts. And this is what we also have calculated. So if I use this formula now, and then substitute from the simulator the data, and I will get 204.5 milliamps, exactly actually what we have determined in our calculations. This is also the plot you can generate in the SPICE simulator. I will also show you how you can do that. You can see the load current here, the load power, and the load voltage. You can see the load current is indeed start at some maximum value when the load resistance here is swept from 0 to 100 ohms. It starts at 0, and then you can see then the current start at 136 milliamps, but then it keeps decreasing, of course, and it will decrease actually asymptotically to 0 when you increase your R load to infinity. What you also see from the load voltages, it also starts at 0 origin, as we have discussed also in the general case, and then keeps increasing and then gets its some value for 100 ohms. But interesting thing is load power. Load power is increasing and then gets some maximum value and then decreases again. And this is happening at 44 ohms, and the value is 204.5 milliwatts. So you can see it is not just increasing the load resistor in order to get the maximum power. You only get it when the load resistor is equal to the Thévenin resistance. Let's also generate these tables also in the TINA TI SPICE simulator, so you can see how you can do that yourself, and you can also work out more analysis there. So let's now jump to the SPICE simulator. Alright, you are now in the simulator. This is the circuit already prepared and also discussed in the slides. So previously we see the voltage source and the resistance and also the load, which was 44 ohms as calculated. Now if I now check this using DC analysis and just do only the calculate node voltages operation, you see directly actually the 3 volts and also 68.2 approximately milliamps here. You can also click on it. You can see also specifically for this load, you can see the arrows going down. But what we were interested in, of course, is not only the current and the voltage, we also want to see the power plot. So how can we do that? You can do that using the analysis and then DC analysis and DC transfer characteristics. This is a very helpful, let's say, option to see what's happening when you change a value of your component. Now, then you get this screen and you can now change, for example, here what your input is. So this is the thing you are changing, and these are the outputs. So you get the current and also the VL, the load voltage, as the output. I can also say I want to change R1 or any other. So I will change, of course, RL from 0 to 100. That's the choice. You can also type here something else. You can say I want to go all the way to 150. It's really depending on what you're interested in. So let's again do 100. These are the number of points to make it more accurate. So This is, I think, fine, 30,000. And let's now generate the plots for these current, load current, and the load voltage specifically. Now, that's going on. These are the plots. Now, let's separate them. So you go to View and separate curves. And this is the load current. This is load voltage. Now, I will give this the pink color as we have used, and this I will give the blue color. Okay. Now, what you see, I also want to say that this is the load. And I also want to change here a number of ticks to see also this in more detail. Okay, this is load current, this is the load voltage. Okay, let me also make this blue, so everything is set. Now, if I now make this larger, let me make this larger. And I want to actually also see the power, because power, we know, this is IL times VL. So we need to actually multiply each point. And we can do that, and let's actually do the simulator for ourselves. So you can go to the post-processing in Tina TI Spice. You get this screen. Now what you need to do is, you need to add these two here, and also here. And then actually get IL times VL in the function here. So I will just make here load power, just a function, and then say I would like to have this. Let me go back actually, because I think I need to keep it here. So here and this here. So I just click on each of them and then click down, and I also click on the middle here and then select the operation, which is multiplication. So you can see here the star. So you can see IL times VL. That's the result, that's the power. And you can give it any name you want here. So load power or whatever you want. And if I now create this, it will be created, so it will be calculating everything. And I am done. And then you get now also another curve. So that was in our case red. So let me make everything red. So for the comparison, you can see that 204.5 approximately milliwatts, and that's happening. You can see that also better by clicking on the cursor, A or B doesn't matter, and on that plot, and then go to this and the right mouse click, jump to global maximum, and it will give you the maximum value of this plot. You can see it's 44 ohms, so because that's the X value, and it will give you 204.545 milliwatts. So very close to what we have calculated. This is indeed also what's happening. And if I now do label or legend, and then specifically for this case, and let me make this a little bit larger, maybe 18 or 20, but let's do this. You can see also that the VL here is 3 volts at this specific 44 ohms, and the current was 68.2 approximately milliamps. So you can see also that indeed that is also true. So again, this label here will give you indeed the maximum power. So we have now also have verified that it indeed 44 ohms was indeed the maximum, the load resistance to get the maximum power transfer. And you have also seen how you can generate this plot in Tina TI Spice to also verify your findings, your calculations. Alright guys, this was for this example about the maximum power transfer for this specific circuit. This can be done for any other circuit. It really depends on how you work out the steps. So this can be also much complex circuit, but the steps are really the same. You do actually step by step and you work towards the equivalent circuit. Could be of course Thévenin's equivalent circuit or Norton's equivalent circuit, depending on what you prefer. And you need to find then the required load resistor to get that maximum power transfer. If you have any questions, comments, please let me know and I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video. Take care.